You gotta know how things work, okay? So a battery has a cathode and an anode and electrolyte in between, that flows between the, carries iron. So the cathode is a salt. Not surprising, so that's why I got interested. It's lithium cobalt oxide. And so it's layered, all right? There's this cobalt oxide layered with lithium. And the lithium ions flow over here and they fill it up until it's all like that. So before you filled it up, maybe it's X empty, and you need X lithium plus ions in some kind of organic organic electrolyte, all right? Water won't work, so you use some kind of organic electrolyte. So if you got lithium that you got to extract after you got to extract it out of the lithium organic electrolyte. We know how to do that. We've already built the equipment to do other things. Then we just burn off the organics and you're left with the lithium. This one's harder. Okay? On the anode side, you've got lithium now layered with typically with graphite. We use graphite, so we know about this kind of stuff. And so you have X amounts of graphite that you bring over lithium, and you have X lithium. Well, this thing we know how to burn in our so-called charcoal fines oxidizer. We can extract the lithium over here. Here's the difficulty. Get this one out. The chemical way is to have something stronger than oxygen as the oxidizing agent. That's fluorine. That's the simplest. Well, fluorine chemistry is exactly what's used in the molten salt reactor. So I think we would know how to help these guys to do that. So you need to do that. Let me just tell you, give you some impression of the magnitude of the problem. If you recover 90% of the lithium, you're still losing it at 10% of all. Nobody has ever recovered at any recycling program that's better than 90%. So you got to beat that. If you're only 10%, it's not a tenth of 1% problem. It's still only a 1% solution. You got to, be 99.99% recovery. Right? We're the only ones in the world I know that talk about that kind of level of recovery. So anyway, I think that other people would be multiple. And then you got to do it if you're going to rely on anything like this. Nuclear power, we have the same problem. Okay? So here's the calculation. The proven reserves of high-grade uranium ore is 5.5 million metric tons. That's how you measure things. The current light water usage, nearly 400 reactors, is about 0.07 million megaton. That provides about 4.8% of the primary energy use. So the current lifetime fleet could run at 5.5 divided by 0.07. That's 79 years. That's a standard number that the Department of Energy gives you. So how long can we use the uranium? Oh, we got plenty, 80 years. Okay? But that's assuming you don't need any more. Okay? If you don't need any more, you're only getting 4.8%. What's the other 95.2%? Why not make that 100%? Forget nuclear reactors. Okay? The problem is, there's nothing that can supply the 95.2% today. And so if you use nuclear today, a lot of people are talking about expanding light water reactors. You make them smaller, they become more economic. How does that help? You need to burn a certain amount of uranium to get a certain amount of energy. It doesn't matter if I burn in small packages, big packages. Those things are not addressing the problem that we're concerned with. All right? So if you want to do it at 100%, how long do you put it? At 4 years, I just mentioned. Okay? So the solution is, again, recycle, reduce the cost of manufacturing. So when people talk about things being, batteries being cheap today, they're talking about the cost of manufacturing. They're not talking about the loss of material, the aspect of recycling with zero waste. We've got to change that whole way of doing business. The whole way of doing business today is I have some resource, I have some process and I have some waste. The waste, oh, that's somebody else's problem. Stop that kind of thinking. That's your problem. That's our problem. Okay? The only way to become sustainable is zero waste, in my opinion. Okay. Thank you. Any questions?
That's not a solution.
What's not a solution?
No, we can't get to zero waste.
No, you get to 99.9%. It's good enough.
Yeah, but how?
That was last time's talk.
Right, I mean, like the uranium, that's just not gonna work.
No, so you use thorium, you use 100% of it. You don't use 1% of it. That gets you
But it
to
cannot be uranium.
right?
It cannot be uranium.
You can do it with uranium, with fast reactors, okay? The problem with fast reactors is that they require such a large inventory per reactor, you can no longer do it in the time scale that's left. That's my personal opinion. So you have to go to thorium reactors. Something that you can do with thermal spectra. Then you can do it. You bring that curve, that CO2 curve, slowly to zero, and then you use biomass to bring down the,
So how fast do we have to bring the thorium online?
how fast do we have to what?
Bring the thorium reactor online.
That's how many reactors do you have to build,
Every day.
okay? Roughly speaking, depending on how big you make them, it's thousands to 10,000 reactors. So, roughly speaking, it's one reactor per day somewhere in the world you gotta build. Okay? You say, well, is that possible? The answer is France did it after the first oil crisis. When you scale France, that's a scale you need. So it can be done. And these reactors are, in some ways, simpler than the current reactor. So let me see if I can come to that. It's not a trivial thing, but it's doable. You need a company like Boeing or something that mass produce these kind of reactors. It's not going to be easy. Nothing's easy now. There's no easy way out, you know. But what's the choice? The choice is either the vanishing of civilization, or you go this route, or some route like it. So here's that curve. Okay, so this is what you need to do. Go up there, flatten it with new nuclear. You know. Now, the rate we make cars is much larger than that. And I'm talking about something the size of a car. Cars are made at rates much, much higher than you need to make these nuclear reactors. A nuclear reactor is not very difficult. I told you, it's just pipes. If you don't worry about generating electricity. Just pipes and pools. It's easier than a car in principle, once you start mass manufacturing it. It's public acceptance, government backing, that's black. You don't say, well, how long does it take to build a reactor? Well, when we knew nothing, Fermi could do it in 6 weeks. Okay, nuclear reactors are not hard to build. Now we know everything. It takes us 10 years. How can this, why is that?
Well, it may be fast to build, but it takes so long to license one, right?
Yeah, it takes a long time to license them. That's a problem. And who made it difficult to license? Okay. Nuclear reactors have a lot of values that people don't like. You know, you can look at the choices. What are you going to do?
So there's a piece by Ernie Moniz I read today, where he claims that there's 50 kinds of nuclear reactors being worked on.
Yeah.
Is that right?
Right now, nuclear reactors, except in France, are built one by one. Okay? And that's the way the US did it, which means every single one has to get reapproved. All right? And that's obviously not a good model. You obviously want to put them on a production line. Now, you may have several such production lines in different countries, but basically, mass manufacture. That's got to be the way to go. There's no other way to do it. Let's see. I have that slide. So you can see the choices that you can make in terms of different kinds of nuclear reactors. So right now we only use light water reactors with a little bit of graphite and heavy waters, but mostly light water. So in each line you have various choices. You can have a burner, you can have a breeder, you can have hydrogen versus deuterium versus graphite, etc. So you know, this is 3 times 3 times 2 or 3. No, you just go down there. Never mind manufacturing techniques. There are literally thousands of kinds of reactors you can build. So I've given you what I think is the absolute best reactor. Okay? If you don't like this one, forget nuclear power. That would be my statement. Right? Not going to be much easier. It's not going to be easier any other route.
More questions?
So what's the physical reason that make a S diagram a line, a curve, instead of?
It's a theorist. There's obviously some variation, but on a log plot, the error the variation is very small. It's factors of 2 or 3. We're talking 16 orders of magnitude or 12 orders of magnitude. Yes, there's some variation. Different batteries are different, but it's the fact that there's the 3 regions is physics and chemistry. Okay, so I'm not converted to MKS because that's what engineers use if they don't use English. So why do we use joules? Because mechanical energy is easily expressed in joules if we talk about motions that is familiar to in everyday life. Why do we use liters? Because liters is something that you can imagine, right? It's a quart. So things like uranium or chemical energy, this is 1 million times that, and this is 1 million times that. Why is that? It's just because electrons, which in atoms and molecules, are moving much faster than meters per second. They're much lighter than protons and neutrons, which account for the weight. But they move at 1 over, alpha times the speed of light. And that means chemical energy is measured in MeVs per kilogram. Okay? Nuclear energy is in this dense little thing. It's measured in, if you measure it in joules per kilogram, it's measured in terajoules per kilogram. So you naturally find things closer here. And if you have mixtures of the two, or you have especially dense fluid, you're somewhere in between. So that's the basic S diagram, okay? Basically, portion here is a portion here, portion here. If you're not a solid or a liquid, you're over here if you're a gas, at STP. So that's S. It's kind of like main sequence horizontal, that's giant. It forms an S. But when you think about it, think of the S, and think of what Santayana said. We know this. We've known this since the rise of the nuclear age. I'm not the first person to produce this diagram. Other people have produced this diagram, or similar to it, maybe not as complete. But they never asked the physics question. If this is so, how can these things that are orders of magnitude cost the same amount of money? Even within factors of a few. How can they cost the same amount of money? The answer is because generating turbine electricity is down here. So if you use all these good things, you're wasting their qualities, except for lifetime. Of course, nuclear energy can be used very, very long. But nobody does any long-term thinking. So they forget about this diagram, and they don't worry about this diagram. Then you're left with people who are not scientists discussing scientific policy. That's what we have today. You have a lot of people discussing policy, writing blogs. Do they really understand the science behind this? Has any of them actually produced a watt of power or a joule of energy? No. They just got their ideas. But really, you know, if you're really going to discuss it in a rational way, you have to understand the physics and the chemistry behind this stuff. Right? In the same way that you